Okay, so if let's do this. Let's go to, say, question 10. All right, talk to me. Can you guys see this question okay?
No.
No. All right, let me change my screen on the share. Now can you see the question? Yes, good. All right, and Haley is logging on. Haley, can you hear us?
Yeah.
Awesome. Okay, we are looking at some of the homework questions, trying to get ready because the homework is due today, and there is a quiz that you are supposed to take today as well. So let's look at this. For one, most everybody felt like that was a review of chapter 2, and we were pretty good, right? Right? Yes? Okay. So let's look at 4.2. Let me get my stylus. Let's see where I put it. Here it is. And it says 53% of U.S. adults have very little confidence in newspapers. So you randomly select 10 adults, find the probability that the number of U.S. adults who have very little confidence in newspapers is, so on A, let me pull up, well, okay. So on A, we want to find the probability that 5 have very little confidence in newspapers. Now, talk to me about, you remember what this was all about? We were supposed to recognize if this was a binomial distribution. What makes it binomial?
Success or failure. Those are the only two options.
Perfect. So if I'm going to ask somebody, do you have very little confidence in newspapers? They're either going to say yes or they're going to say no. So it meets that condition. And that means that the way that I find it, how many of us, you guys can either show me by a show of hands or you can unmute yourself, how many of us are going to use the formula that we looked at in order to calculate the probability of exactly 5? The one that involved the, okay, so Brandon, are you saying yes, you're going to use the formula that's the, using the combination and the P and the Q?
Yes.
As opposed to the calculator?
That's what I did when I solved this one.
Wait, there's another way to.
There is. Okay, let's do this one.
I've been doing that with the calculator.
You have been doing it with the using the formula with the calculator? Okay, so yes, there is a formula, and it is taking a combination, I'm going to write it up here, of n things taken x at a time, right, times the probability of success to the x power times the probability of failure to the n minus x power, right? Okay, so doing this by hand or using the formula, that would mean we're going to have a combination of what's going to be my n in this problem?
10.
10. And what's my x?
53.
Well, my x is actually what? Hey, Huckabee. 5, right? Because I want the probability of exactly 5. My P, my probability of success is what? So we said n is 10, x is 5, P is what?
0.53.
Good, 0.53. That means Q is 0.47, right? Okay, so we're going to have a combination, 10 things taken 5 at a time, times my P is 0.53 raised to the what power? Using this formula here. What's going to be the exponent?
5.
5 times my Q is what? 0.47 raised to the 5, because 10 minus 5 is 5. Okay, now let me pull up the calculator. Okay, and here's what we're going to do. We're going to calculate doing a combination. We say we can find that if we go into math and we arrow over to prob and we choose 3 and we'll put in 10 here. We'll put in 5 here. And then in parentheses, I'm going to put, what is my P? 0.53 raised to the 5th power, arrow over, and then we'll put in 0.47 raised to the 5th power. So that's what it would look like if I plug that formula into the calculator, and if I hit enter, what do I get? I hit enter.
0.242.
Right, so here's what we're going to need to do. Let's go back and look at this problem. Okay, and it says round to 3 decimal places. So I had 0.24 and then I think it was 16. So what am I going to put in for the next digit?
2.
2. All right, let's check this. That is correct. Now, can somebody tell me, before we do the next one, how could we do the probability that x equals 5 by just using the way the graphing calculator is programmed? You remember what we do with that?
Second vars.
Yes, we've got to go into those distributions. So it's second vars, which gets us into distributions, and we choose binomial PDF.
PDF. Because that's for just one number.
And so I'm going to take you back to the calculator so you can see. Hang on.
PDF is for one number. CDF is counting up from 0 to that number.
Excellent. So we are going to second vars, and under distribution, we arrow down till we find PDF, binomial PDF. Oops, went too far. Back up. It's a lot easier on the regular calculator than it is on my screen. Okay, so I'm going to hit enter. And trials is what number on this problem?
10.
Excellent. And then the p-value is
0.53.
very good. And the x value is 5.
5.
Right? And I don't have to put in Q in the calculator because it can automatically calculate the Q when I tell it what the P is. It pastes it into the binomial PDF function for me. And did we get exactly the same number?
Yes.
It is your choice. You can use either the formula that we did the first time and manually calculate the pieces, or you can go into second vars and choose binomial PDF and do it that way. All right, any questions? That makes sense, right? Okay, so let's look at, no, I don't want that. I want, let's see. We'll go back to this. And now the next question says, what's the probability that x is greater than or equal to 6? Now, if x is greater than or equal to 6, that means I'm looking for what?
6,
7, 8, 9, 10.
All right, so that would be the probability of 6, 7, 8, 9, 10. And if I do the formula, how many times am I going to have to compute that? 5 times, right? Because I got to do that formula for each one and then add them all together. That's okay to do it that way, but is there a shortcut if we use the binomial CDF? And I kind of bet JT knows something about that. What would you do?
Binomial CDF of 5 and then 1 minus the answer.
Okay, so here's what JT is reminding us. Our binomial CDF adds up from 0 up to whatever number that we want. So if we found the probability that x is less than or equal to 5, that's going to take the probability of 0, 1, 2, 3, 4, 5, add them all up. And if we subtract that from 1, that would equal the probability of x being greater than or equal to 6. Make sense? So by using that shortcut in the calculator, instead of having to compute the individual probabilities and add them up, I can find this one cumulative. That means I want a binomial CDF and take that number and subtract it from 1 using the complement. Does that make sense? Y'all give me some sort of signal so I know. Okay. All right, and it's okay to do it this other way. It's just going to be faster if we did the binomial CDF. So, and since we've had a few more people log on, if you're not aware of this, Brandon's mom said she would be happy to try to get some of the graphing calculators for those of you who might be at home without them. I know Seth and Trent need one. How about the rest of you? Is there anybody else who's going to need to borrow a graphing calculator to finish the course? Haley, do you have one or do you need to borrow one? You'll have to unmute yourself so I can hear you.
No, I have one. I already got one from Miss Putman.
Okay, awesome. How about you, Hagabet? Do you need one? You do? Oh, you've got one. Okay, good. Sydney, what about you? Sydney, are you there? Hello, Sydney. Let me see if I can get to her on a chat. Okay, I'm going to send her a message and then we'll get back to the rest of this problem. Okay. Ah, I see. Sydney says yes. Okay, perfect. So that means 3 of you guys. And does anybody know, since Abigail's not here, does anybody know if Abigail would need one? Any ideas? I'll send her a message. We're also missing 1, 2, 3, 4, 5, 6, 7, 8. Who else are we missing? I'm trying to think. There's one more person. Okay, I'll check back on the roll and we'll see. All righty. So, yes, Troy, thank you. I think Troy probably has one, but I'll double check. Okay, awesome. All right, so let's do this. Can you tell me if I pull up the calculator, and I'm going to clear this off right now and make sure you guys can see my calculator. Okay, tell me where I would go if I want to get that binomial CDF that would add up everything to 5. Tell me which buttons to press.
Second vars.
Okay, second vars. And then what?
Go down one more than this one.
To binomial CDF, right? Okay, and tell me what to type in. Trials is
10.
10. P is 0.53. And what goes in for X here?
5, because we're looking for 6 and up.
Very good. Now, here's what I got to be careful about. When it gives me this number, is that my answer?
No.
No, that is the complement of my answer. That means if what I want to happen doesn't happen, that's the probability. So to get the answer I need, I do what with this?
1 minus upwards arrow, enter.
Exactly. I can do second answer and enter, and I get 0.45262. If I enter this in 3 places to the right of the decimal, I'm going to be putting in what number?
0.453.
Are we in agreement on that? Very good. You can, again, you can do each one of those manually and add them up, but this is a little bit faster. Okay, how would we get the answer to the probability being less than 4?
Binomial CDF, 3.
Okay, JT is saying he would put in binomial CDF and then he would use an X value of 3. Do you agree with that? And I want you guys to use that chat button and either answer yes or answer no, if that's the way you would do it. What do you think? Okay, got 1 answer, 2, 3. Good. Okay, so it sounds like you guys pretty much on top of that. So if we went to binomial CDF and we put in 3 as our X value, by the way, why wouldn't I put in 4 on this one?
Because it's less than 4, not equal to.
Very good. If it had the or equal to, I would use 4, but since it doesn't, I can only go up to 3. So to save time, since you guys, we've already been through that, I'm going to assume you're good. We won't do that one. How about, is there anybody who has, do you remember a homework question you might want to look at out of 4-2? Number 1, or you got a question, Seth? No?
One moment, I'm looking for it.
Okay, so Seth's trying to find it. If anybody else knows that you've seen one that you want to go over, let me know.
On number 19, it was telling me to round up to the nearest 10th. But even when I had numbers like 1.06, it would say the answer is 1.0.
Okay, so let's check on that and see. So this is saying 76% of US adults think political correctness is a problem. You randomly select 6 adults, ask them whether they think that's a problem or not. The random variable represents the number of US adults who think that political correctness is a problem. So first of all, we have to find the mean. Now, that had a formula for us for if it's a binomial probability distribution. Now, do you think this one is? Is it a binomial probability distribution? Okay, I see a thumbs up from 3 of you guys. The reason is, if I ask the question, do you think political correctness is a problem? I get either an answer yes, which is a success, or no, which is a failure, based on the fact that 76% think that political correctness is a problem. So that means it is a binomial distribution. What's the formula to get the mean when it's a binomial distribution?
Times P.
N times P. Now, you tell me from this problem, what is the value of N? N equals
6.
What is P?
0.76. And when you multiply those together, you get 4.56, which comes out to 4.6.
So 4.56 is what you get when you multiply these two together. You guys agree to that, right? So if it says round to the nearest 10th, let's see what happens if we put in 4.6. Okay, so it took that one. Now, to get the variance, what is the formula for variance? You remember it? It's on your formula sheet if you need to go back and look at it.
As Seth said in the chat, N times P times Q.
Thank you. I appreciate your keeping an eye on that for me. So I need to identify Q, and if P is 0.76, Q would be 0.24, right? So I'm going to go ahead and use my old school handy dandy calculator as well, because it's a lot faster than the on screen. But if anybody wants me to do something on screen, you can tell me. And I've got 1.094.
So
Okay.
1.1.
All right, so we're all in agreement this should round up to 1.1, right? If we're rounding to the nearest tenth. Let's see if it takes 1.1. And it did. Let's see what happens then on the standard deviation, because when it's standard deviation, we have to do what? Take the
Square root of variance.
That's right, square root of our variance. So if I take the square root of this number, let's see.
1.4.
Okay, so this looks like 1.046. So if I were to round this one to the nearest tenth, it's going to be what?
1.
And can I just put in 1, or do I have to put 1.0?
You can just put in 1.
Well, if I'm rounding to the nearest tenth, I should put in 1.0. Now, I don't know specifically what it would do if you tried to put in 1 without the 0.0, because this didn't come out to be exactly 1. So if it told me to round to the nearest tenth, I really need to put that 0.0 there to indicate it was rounded. Okay, so it
It'll
took
take
all
that.
of these here. I don't know if you had something that was kind of quirky on your Seth. If that runs into, like, if you have that happen again, then send me a message and ask my instructor and say, would you please look at this? And then that way, if it's telling you it's wrong when it's really right, I can go in and manually fix it for you. Okay. All right. Anything else you guys can think of you would want to look at from homework? Or are we feeling okay with 4? Oh, we do have one more. Sorry. All right, see if you can answer this one. Most samples of 6 adults would differ from the mean by no more than what?
1.
Because if I'm talking about how much I'm different from the mean, that's asking me for standard deviation. Okay, and that's what it's checking to see that you know. Okay, so we ready to start 5-1? All right, quick question. How many of you are doing okay watching the videos, as far as, for the most part, you feel like you understand everything from the videos, versus how many of you either have not been able to watch them or it's not working for you? And I've got the chat up so I can see it. So if you want to just send me a quick message, you can either, tell me video's good, or can't watch them, or still need help, just so I kind of know what's going on. Okay, so I got a message from Trent. Okay, so far so good. Okay, so if you end up with any issues, don't hesitate to let me know, because we can go over them in class, but we can also do some Zoom meetings for tutoring if we need to. So what I think I'll do is, let me pull up the PowerPoint. I keep hitting that by mistake. Let me pull up the PowerPoint, and we'll kind of hit the high spots and just do a real quick overview of what we're going to be doing in this lesson. So we're going to be talking about normal distributions, and we've already had some conversation about normal distributions, have we not? Can you guys all see this slide? Did I lose you? Or are you still there? You may have to unmute yourself. For some reason, I'm not seeing your screen. Where'd y'all
I
go?
can see it.
You can see me? Okay, and you can see the slideshow. That's really odd. Where did it go? Okay, well, I'll just roll with this for now. So the difference is, you remember at the very beginning of 4.1, we talked about the difference between a variable being discrete versus continuous. And we talked about things like, and in fact, it's back up again, where if we were looking at the number of phone calls maybe that you made in a day, if you had to report to your employer, how many sales calls did you meet in a day? Would that be something that's discrete, or would that be something that's continuous? What do you guys say?
Discrete, because you can count it.
Exactly. If it's a countable number of things, then it is discrete. But if you were to instead report how many hours did you spend making those sales calls, then what would you say?
Continuous.
It would be continuous, because that's not a countable number, because there's all kinds of in-between values between 1 hour and 2 hour. So where binomial distributions are for data that's discrete, okay, we're going to now shift gears and look at when data is continuous. That's going to give us a normal distribution, that bell-shaped curve that we talked about before. So when it's continuous, we know there's an infinite number of possible values that can be represented on a number line. Okay, and let's see. The probability distribution of a continuous random variable is a continuous probability distribution. So we're going to take that, and if we graph it, we're going to call it a normal distribution. It's the most important continuous probability distribution in stats. That's going to be the one that is used far more than anything else. And the graph is called a normal curve. That bell-shaped curve, we would say, is a normal curve, okay? In a normal distribution, the mean, the median, and the mode are all equal. We know it's bell-shaped. We also know it's going to be symmetric about the mean. And the total area under the normal curve is equal to 1. Now explain that to me. Why would we say the total area is 1? Because 1 is equivalent to what percent?
100.
100%. Very good. So when we're looking at area under the curve, it's going to have to be some value between 0, which means nothing, up to 1, which means the entire thing. Also, the normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. Now, if you guys can think for a minute about some things you would have, let's say some vocabulary you would have learned in algebra. What do we call it when we have something that's getting closer and closer and closer to, say, the x-axis, but it's never going to get there? Starts with an A. You have a asymptote. Remember that? So in essence, it never actually touches the x-axis, but it's just going to get closer to it. The area under it is so small, it's almost impossible that you're going to have any data that would be there. So let's back up a minute. We'll talk about what we covered way back in the end of chapter 2. Well, actually, this may be the part that we kind of said we'd get to later. You remember how we said that we had the empirical rule? Everybody remember that? The empirical rule that told us about what percent of the data should be between, say, 1 standard deviation of the mean versus 2 standard deviations and so on. You guys remember that? I'm going to need, okay, I see a chat coming up. Yes, okay, good deal. And when you say 34% thing, then you're saying that 34% would be maybe between the mean and 1 standard deviation below the mean. you're absolutely right, because 68% is within 1 standard deviation of the mean, either above or below. And then 2 standard deviations is going to have, anybody remember what percent?
95.
Excellent. Thank you, JT. And then when we got 3 standard deviations from the mean, we had, anybody remember?
It was like
99.7.
7.
Okay, so that's practically everything within 3 standard deviations from the mean. Now, the part we didn't really talk about, you see where it's marked that it says inflection points? Unless you've had pre-calculus or calculus, you probably haven't talked much about inflection points. They're really helpful pieces of information, though. Do you know what an inflection point is? Anybody? You'll have to unmute yourself so I can hear you. Okay, so I guess you want me to tell you, so I'll just tell you. An inflection point is where you have a change in what we call concavity of the curve. Let me stop for just a second and get back to where you can see me. So, any contact lens wearers in here? No? All right, so if you're a contact lens wearer, I'm betting when you get that contact lens out of your case, you do this and you look at it before you pop it in your eye. Why would I do that?
So it's not on backwards.
Do you know why I wouldn't want to put it on backwards?
Because it only works one way.
Well, it's not as much that it won't work the other way, but boy, it does not feel good. Okay, because the contact lens, if I put it on the right direction, it's going to be shaped like this. It would be concave up so that it would cup onto my eye. If I don't put it on the correct direction, what happens is at the very outer edge, it kind of curves out. There's a change in concavity, and that hurts if you put it on because it irritates your eyelids. So concavity is that point where the curve, it's not that it stops increasing, but it changes by the amount that it's increasing. That's what an inflection point is. So if you think about, and I'll just give you a quick example, say from the world of business. If you were let's say you had a business and you're tracking your profits, and you've got profits that are increasing, and it's doing this, okay? And each month they start increasing more and more and more. But guess what happens when you're still increasing your profits, but the amount that it's increasing starts slowing down? Instead of doing this, my curve is going to start flattening out. Right now, this is a great illustration of this with what's going on with coronavirus. Have you heard the phrase flatten the curve a number of times now? Absolutely. And what is it they're trying to get us to do? What does that mean when they say flatten the curve? Do you not know?
Less and less people having it.
Okay, because what it's going to do, now if you're looking at this screen, would you say that this thing has a pretty stiff peak? Yeah, I think it, can you see that normal distribution I've got on the screen? I can't hear you guys. Can somebody answer me?
Yes, ma'am.
Okay, thank you. And so what happens when you've got this flattening of the curve is they're wanting you, that did not do what, okay, hang on a second. Let me go back to, no, I don't want to do that. Hold on. Technical problems. Let's go back to this one. Okay, so tell me, do you see, Okay. Tell me what you're seeing on your screen. Do you see the one that's still got the little slides off to the side, or are you seeing a different screen? Do you still see the curve on your screen? That bell-shaped curve, and it says total area of 1. Can y'all see that or not?
Yeah, we can see it.
Okay, thank you. So what that flattening the curve is talking about would be, instead of having this inflection point, do you see how this is concave up? And then there's this point in here where it does start to slow down, and then when you get to the peak, then you would say instead of increasing, the whole thing is decreasing. So this inflection point is kind of important because it's a signal, and they're talking about this when they do these coronavirus news conferences. It's not that the number of new cases is not continuing to happen. It's the idea that it's not growing as quickly as it was, and that lets you know you're getting closer and closer to the peak, and that's how they're estimating when they're going to get to that peak. What they're really hoping we're going to be able to do is the idea of this flattening the curve, that instead of going up where it's going to be a peak there, that maybe it'll do something more like this. That's making it not such a steep peak. It's going to kind of tamp it down. Okay, so that's the idea behind the flattening the curve. Now, let me get back to where we were. And let's talk about this probability density function, a PDF. Remember, we just looked at a binomial PDF, which was when we had discrete data. And so that binomial probability distribution or density function had to do with that. A probability density function means that we're going to have two requirements: that the total area under the curve is equal to 1, and the function can never be negative, okay? And as long as it's continuous data, then we'll be able to get this probability density function for a standard normal curve. Now, this kind of explains even better than what I was showing you a minute ago, the flattening the curve idea. These are 3 normal distributions where they all share something in common. If you look at the first 2, is the mean the same? On curve A and curve B, is the mean the same? What do you guys say?
Yes.
Yes. And the issue is what's different is the standard deviation. Agreed? Because on the first one, the standard deviation is 1.5. On the second one, the standard deviation is 0.7. Now, tell me how you would describe the difference. If the mean is the same, but these two do not have the same shape, what difference does it make when my standard deviations are different? What would you say occurs? If the standard deviation is bigger, then what's going to happen? The data will be clumped together or more spread out?
Your inflection points are going to be at different places because it's more clumped if it's smaller.
You're right. Your inflection points are going to be at different places. And the key is, if my standard deviation is larger, oops, I don't want to do that. I want to do this. If my standard deviation is larger, like it is here, that tells me my data will be more spread out. And if my data is more spread out, then that's the flattening the curve idea. And that's what they're looking at. When we start getting a smaller standard deviation, it means all of a sudden all these people are getting sick at the same time. That's when you get that real steep curve. And it's going to give you that high peak because you're going to have too many people sick at the same time, and the hospitals can't handle it. So they're applying statistics right now to what's going on so that they can make it more manageable. Does that make sense? it's kind of interesting to be able to look at it from something that's going on in the world right now. Now, if I look at the last two curves, the B and the C, do the shapes look the same? That's a yes or a no. What do y'all say?
Yeah.
Yeah, the shapes look the same. But and because the shapes look the same, it's telling me my standard deviations are the same. But what's different about the means?
How high they go up.
Well, actually, these are going up to the same height. The difference is where it's positioned along the x-axis. The mean is going to be the average of my x's. And so on graph B, my mean is at 3.5, but on graph C, my mean is at 1.5. My spread is still the same. It's just the mean occurred at a different place. Okay? So that's what I would look at when I'm trying to figure out what do these things tell me about the data that I have. So if you look at, and let's do this. Well, hold on. Why is that not opening up? I'm so sorry. I'm having so many technical issues right now. Okay, so now let's try it again. If I do this and this, no, that's not what I wanted to do. Okay. Well, we'll just roll with it. Okay, so if y'all were asking you between A and B, which one has the greater mean, what would you tell me? Clearly A, right? And why would that be the case?
Just where the center of it is.
Exactly. The mean is going to be where the center is of the normal curve. And so it looks like my mean is about 15, right? Now, if I were to ask you which one has the bigger standard deviation, what would you tell me?
B.
B, because the curve is flatter, right? The data is more spread out. So that's the whole idea. If we can spread it out more so we don't get too much clumped together, we'll be better off as far as it relates to coronavirus. Now, what I want us to look at real quickly is how we can convert data to be able to look at it as a standard normal distribution. And let me just kind of give you a quick idea of why that's important. So let's say we were trying to compare the data. Well, in fact, let me see if I can stick with this coronavirus thing and give you an illustration. When it first started happening, did you hear some comparisons where they talked about it being kind of similar to flu, right? Right? Yes. But then they came out and said the problem is it's much more contagious. Agreed? That became part of it. So in order to get a comparison of data, you've got to be able to do kind of an apples to apples comparison. And so they had to come up with something that would let them, be able to look at, okay, we have this many cases of flu, and the number of people who contracted is this, and so forth and so on. And so you have to come up with something that's going to give you a better idea of how these two things really compare. Here's another way that you could think about trying to get what we would say is an apples to apples comparison. Let's say you had an overweight elephant at the zoo. Okay, They just are outside the bounds of what it is to be healthy. And you've got an overweight person, and you're trying to determine which one is actually more overweight than the other in comparison. Now, an elephant has an average weight of what? Some thousands of pounds, right? I mean, definitely a whole lot more than what a human weighs. And so I can't just look at what the weight is for a normal elephant and the weight for that elephant and compare it to the difference that I would get for humans, right? There's got to be some tool that's going to let me be able to compare which one is actually more overweight than the other one. And that's where the standard normal comes in, finding what we call a z-score. It will take something and standardize it. How many of you guys took ACT, SAT tests?
I did.
Yes, no, maybe? What'd y'all do?
I
SAT,
took the SAT.
ACT? I don't hear you. Are you still there?
Yeah.
Somebody unmute yourself for me. I need to hear you.
I've taken one.
Okay, you're chatting. I really like it. Okay, so yeah, I think I did. I took the ACT. So here's the issue with that. They give you a raw score, like a good score on the SAT, since I think they've gone back to 1600 as being the top score, would be maybe 15 something. That'd be a really good score on the SAT. But do they also give you a percentile that lets you know how you did in comparison to everybody else? And actually, your raw score is different from like that 1500 or 1400 or whatever, because they then convert it to a scale that would let you compare it to other people. Okay, so you have to go back and come up with something that's going to let you standardize it, because when you take, say, the SAT, is everybody's SAT test exactly the same questions? The answer is no. And so some questions are a little bit harder than others, and that's what they do to standardize it, to come up with a standard score. And here's how we're going to do that when we need to make those comparisons. If you take whatever your X value is, that you're, like if we talking about the weight of an overweight elephant, we take that elephant's weight, we would subtract the average weight, the mean weight for an elephant, and divide it by the standard deviation for an elephant. And that would give us a z-score that would give us a way to then compare to the human if we use those values for the human as well. Okay? And that way, you don't have to have two things that already are identical to be able to make a comparison to see, which one is actually more out of line than the other one. So what we're going to do is practice taking data that's given to us with X values and mu's and a standard deviation, and we'll convert them to a z-score. And that z-score will let us then standardize everything under the normal curve. Now, when it's standardized, because the entire area is 1, then we're going to set it up so that a z value of 0 is the mean. It's right in the center. And then we're going to, actually I shouldn't say the z value is 0. The mean is going to be 0. I know they wrote z equals 0 on there, but the z-scores are going to be 1 standard deviation above and 1 standard deviation below, okay? And then 2 standard deviations above and 2 standard deviations below. By the time we get to 3 standard deviations, should we have pretty much gotten all the data under the curve? Yes? Yes. But what we're going to do is realize it definitely can go further than that. But if we were looking at the area under the curve, everything to the left of a z-score of 0 is going to be 0.5. Everything to the right of a z-score of 0 would be another 0.5. So under the whole curve, we've got an area that's close to 1. Okay? Now, let's get to the next one. Let me kind of scroll through. This is, again, if we were reading a table, but that's so outdated. We're not going to do that. You can do it in the homework if you want. It's pretty easy to see how to read it off a table, but it's so much better to me using the calculator. So what we're looking at would be how we can find area. Well, I say that, and you know, I usually have some students who do want to read z-scores out of a table. So I will show you how to do that. Let me back up a second and remind you how this, or at least explain how this would work. So when you get a table like this, if your z-score is 1.15, since it's cumulative area, it means all the area to the left of 1.15. So on this table, you have everything to the nearest tenth going down in the first column on the left. So you would find 1.1, and then when you go across the row that's on the top, you would come to 0.05. And where those two intersect would give you the area for everything that would be to the left of a z-score of 1.15. So that's how I could come up with finding my probability distribution. If I wanted to know the probability of some x value being less than some number, as long as I know that x value, the mean, and the standard deviation, I can convert it to a z-score, and then from this table I can get the area, which will tell me the probability of something being less than that amount. Okay, now that's if you use the table. If you want to use the calculator, it's actually, I think, very easy to do that as well. And I'm going to show you that. But you also need to know we can still find area to the right, and we can find area between two z-values. And the area between two z-values is definitely much easier to use the calculator, because if you're trying to do it out of the table, I'm going to have to look up the area at negative 0.75. I'm going to have to look up the area to the left of 1.23, and I would have to subtract those two in order to get my answer. So let me show you real quickly. If I go back to the graphing calculator, let me get that screen up. Okay, actually you guys can see it, right? Okay, so the way we're going to do that is just like what we were doing with binomial CDF. Go to second bars, but look at what's at the very top. What do you see? Somebody speak up so I can hear you.
Normal PDF.
Do you see normal PDF and normal CDF? Oh, come on. Have I lost you? Speak to me. Where are you? Okay. Thank you, Seth. So you can see that there is a normal PDF and a normal CDF. We are actually not ever going to need normal PDF. We want the cumulative distribution because we're dealing with area under the curve, and we want it to add up to whatever value. So if I click number 2 for normal CDF, now here's the nice thing about the calculator. It will automatically default to say, okay, I'm going from the left tail. Now let me show you what I mean by this. If we look at a normal graph, and let's say we get a z-score of 0 in the middle, And I'm doing something like this with my curve, and I know that's a really lousy looking curve, and I want to go to, let's say, a z-score of 1.15. If I want the area to the left of that, then that means I've got to put in my lower boundary, and I'm all the way out in this tail. So I'm going to put in this, and it's defaulted to be in scientific notation, -1 times 10 to the 99th. That's just saying I'm as darn negative as I can get. You don't have to change it as long as you want to go all the way to that tail. My upper boundary is going to be where I want to stop, and I'm going to stop at 1.15. My mean, as long as it's a standard normal curve, the mean will always be 0 and the standard deviation will always be 1. And now when I calculate this, it pastes all that in there. And do you remember when we looked at that graph a minute ago, the area was that 0.8749? We could get it out of the calculator instead of having to look at it from the table. And on these area under the curve questions, when it is a normal curve, you want to go 4 places to the right of the decimal. That's going to be our default. Okay, so any questions on this right now? Okay, so let me make sure. Okay, so we're back at the slideshow. Can you guys see that if I use a -0.99, I can either look that up in the table to see what the area to the left of that would be, or I could go to normal CDF in the calculator, and it's going to give me 0.611 for the area under the curve. Now, if I'm to the left of my mean, I should know that that area is going to have to be something less than 0.5. Agreed? Yes? Because if I put in a z-score of 0, that's right in the center, and it's going to be half of the area. All right? So I'm just going to scroll through this real quickly. This is the part where your calculator is really helpful. Let's see if we wanted to get the area between a z-score of -1.5 and 1.25, how that would work. So let me pull that calculator back up. Can you guys see the calculator? I think you can. Okay. And what we're going to put in is that second vars. We're going to go to normal CDF. And this time we'll put in, and let me look real quickly, I think that was negative, let me go back and look at that for a second. -1.5 and 1.25. Okay. So we'll put in -1.5 and then a positive 1.25. Mean is still 0, standard deviation is still 1, and we get 0.8275 if we round 4 places to the right. Now, notice this says 0.8276, okay? And this is the part that I'll tell you you have to be a little bit careful about. Normally in my math lab, it's already set up for a little bit of variation, okay? And probably if you typed in 0.8275, it would tell you that it's right. The reason we've got 0.8275 and this says 0.8276, think about it for a minute. They're getting their answer from using this table. Look at that table. Do they have values that have already been rounded 4 places to the right posted in there? So on this one, when you're taking the difference between those two, you're taking a value that's already been rounded and you're subtracting a rounded value from it. And technically, our answer is honestly more accurate than what, sorry, I need to get that going again. Our answer is actually more accurate than what the table answer is, but my math lab is programmed to use the tables. So what I'm saying is you probably won't have a problem, but if you do, the best way to fix it is if you need to adjust something. Typically, if you round up by one more, it will be close enough then that you won't have a problem when you enter it. Okay, any questions on this so far? Are we good? Because that's everything that's in 5.1. I want you to see, by the time you finish the 5.1 video and you work on that homework for 5.1, let's see if you have any trouble being able to use the z-score to get area under the curve. Your quiz is due tonight. I do have another question I'm going to ask you guys. I'm looking at a, hold on a second. Okay, I am looking at a an option for testing that will be a, it's called Honor Lock, and it is a third-party testing site where you could use a Chromebook if you have one, but you would need to have a webcam, and you could go in and they would do the proctored testing for us. And so if you've got Chromebooks, and because those don't work with lockdown browser, it would work with this. Does that sound like something that probably you guys all would have access to, that you've got a computer that has some kind of camera with it where you could go in and take your test without having to use lockdown browser? Does that sound like that would work? Okay, I got a thumbs up from Trent. Anybody else? JT, would that work for you? Okay, got Huckabet. All right, good. Haley, what about you? Brandon? See, this is why when you turn off your video, I know some of you walk away. You're not there because I'm calling on you now and you're not there. So anyway, there we go. So Brandon, that would work for you, you think? Okay. So we're gonna, all right, now JT says no. So JT, you're gonna need to send me a message to tell me what the issue would be as far as being able to test. So I'll be able to figure out if we've got a way to work with it or not. It's gonna be not this week, probably next week when we get ready to test. And so I'm still working on exactly how it's gonna play out. And okay, and then JT, I see your message. I don't want you to have to go do that. I'm going to explore the option if you might be able to actually use your camera from your phone. So you wouldn't have to get a webcam. So let me check into that. That's what I'm just trying to find out, is what availability you guys have on different things, and then we'll see. Okay, so 5.1 in the books. You guys are going to work, and if you have any issues, you're going to let me know, right? Okay, everybody's still feeling good? Nobody's sick? All right, good deal. And Brandon, thank your mom for me right now. I know of 3 people who say they would need to borrow a calculator, and I will check with Abigail and Troy, and then I'll probably just send you a message in Canvas, okay? Okay, good deal. All right, y'all have a great day. Enjoy the sunshine while you can, and I'll see you Thursday. Bye.